Hello, good evening. I also tend to speak plus rapide, so to my friends in the booth, wave at me. Est-ce que tu voudrais que je parle plus lentement? That's all the French I'm going to do. I see my good Quebec colleagues back there laughing at my French. Hi, I'm Tim Mihuc from SUNY Plattsburgh. I'm pleased to have even some of my faculty colleagues here tonight, as well as people from UVM and all of you folks from Vermont. I'm going to do this way. As soon as I find my arrow, there it is. What defines a river? So I'm going to talk about ecology of a river. This is sort of the primer intro class on river ecology. What defines a river? The flow. What is flow? Does anybody know? I'm sure some of you do. Q is what we call it in scientific terminology. I don't really have to get into this too much, but if you have a cross-sectional area of a stream, let's say in square feet, you have water moving in feet per second, you multiply the two, you get cubic feet per second, or CFS. That can be translated into cubic meters per second. So we define rivers by their flow. I don't really have to go into this. The previous speaker really talked about how a river works its way through the valley. I'm going to give you some examples of that. We'll focus on the Ausable River, and I'll talk a little bit about some examples from there. This is one of my favorite places on the planet, Cache Creek, Yellowstone National Park. This is two third-order sites coming together. I've been studying this stream since 1989. It was part of my PhD work. And you can see here the river's moving its way through the valley. There's some braided channels here. This is clearly a western river in an arid landscape. It's cutting its way through the valley bottom. That's how it's getting through, getting into equilibrium. This is a great example of a river cutting through its valley, a glacial valley in Alaska. You can see that river meandering. It used to be all over that valley bottom. And the point is, rivers are dynamic. They move. This is Upper J in the Ausable River in New York. Look at this red line here. That's an old river channel. That could have been 50 years ago, and maybe it was 100 years ago. The river used to flow there. It now flows on the other side of the highway. I'm not really going to get into too many of the details of sort of the hydrology and geomorphology of rivers, but I'm going to give you a couple of quick pointers. Most of you that have property on a river, or you maybe have a house or a camp somewhere, know that rivers cut the outside of the edge of the meander bend. If a river's going to cut, the deepest water generally is around here, and the cutting force is typically on the outside edge. So this arrow is the direction that river's going to move in terms of basically taking land away or eroding. If it's a grading, it's depositing that material somewhere else. Rivers usually do that deposition on the inside edge of a meander bend. So there's Geomorphology 101. A little bit more, just pools and riffles. Any of you who fish are familiar with this. I'm really not going to get into it, but rivers are defined by a lot of different microhabitat features, and I'm really not going to get into this one too much either. But those of us that study river systems like to look from watersheds to microhabitats, individual habitats on the tops of stones. There are plenty of things that I work with in the insect world that have flow requirements and substrate requirements that are very specific in the river for certain flow regimes on certain sizes of substrate. You're not getting out of this room with me tonight without talking about some biota. So this is my favorite subject really is aquatic invertebrates that live in rivers. So we're going to talk a little about it. The three main orders that live in rivers are called the EPT, Ephemeroptera, Plecoptera, Trichoptera. Here's the quiz. Who knows what order listed on this page is the single largest, most speciose group of organisms on the planet? Coleoptera, 350,000 species. Anybody work with plants in here? They outnumber all plants. Just the Coleoptera. So if you're going to work with biodiversity, you might want to work with an insect. This describes insect life history. Insects come in two growth forms. Those like the crickets that immature development. The young look just like the adult. They're just little mini versions of it. Or the complete metamorphosis groups, the butterflies, the Coleoptera, the Hymenoptera. The really speciose groups have larval development. The larvae don't look anything like an adult. Then they pupate and have an adult stage. So there's the biodiversity pie of insects and all other animals. The plants aren't on here. And then the beetle coming in, which is the dominant insect. In terms of biodiversity, that's what E.O. Wilson likes to say, right? God had an inordinate fondness for beetles. So the three groups that I'm going to talk a little about are mayflies, A relatively obscure insect group, only 2,000 species. 630 in North America. We've recently completed a study in New York. We've got 179 documented species. They're pretty interesting. They're named Mayflies because they typically emerge in May. They're coming out right about now. Any fly fishermen in the room? You're tying these flies, your duns and your other flies that you're using. One of the main points about this is the economic engine that often drives some of our region is tourism. Some of that tourism is to get to the rivers, to do things in the rivers like fly fishing. These are the stoneflies. They're actually a very good group for water quality indicators. They need pretty much cool, clear, pristine water. They're a pretty threatened group. Their adults are different. They're called the flat wings. They hold their wings flat on their back. There are some of the flies you might tie for those. Last group is the caddisflies. These are the only of these three groups with complete metamorphosis. There's more species here. They have silk glands just like their evolutionary relatives, the butterflies and moths, and they use those silk glands to build cases and spin nets in rivers and do all kinds of crazy things. They're called the upwings because they're like a moth, but they fold their wings up in a tent over their back as opposed to holding them the way a moth does. So here's some of the flies you might tie for that. So, you know, in terms of trout fishing in our region, this is the stuff, the food web, the base that's supporting the trout fishery. And I'll just briefly mention this study that we did. There's Luke Myers, who was the graduate student. He was actually at Colorado State University with the gentleman who's got his head in the pan down here. Luke's the younger one. We did this biodiversity survey funded through New York State by Fish and Wildlife Service funds. And basically, Luke identified taxa throughout the state. These are all the points in the state, and the size of that pie is the number of records in that pie. So it was a pretty good biodiversity survey. I'm not really going to talk any more about it. It goes back into museum collections all the way to 1826 up to present. It was a really fun study to do. Documented all kinds of new species in New York State, and actually Luke's had 5 new species to science from that. I'm not really going to talk a lot about detailed sort of science or hydrology, but I do need to at least point out what a discharge curve is, and I'm going to show you a few more later. Most of you can get on USGS and look at these for the river that's near you. I'll show most of these for the Ausable River, and this is really going to be the focus of sort of the dynamics of what went on in the Ausable. So this is the main stem Ausable after the 2 branches come together. Irene is out here on the end in terms of it's the discharge event of record. This red line is roughly what's considered the 20-year flood recurrence line. And yes, I can count. I know if you count those points above the line, you're going to get more than 5, and this record is far less than 100 years. So I know that means it's probably, that 20-year line probably really is a little bit less than that, based on the evidence from recent climate change since the 70s. It's probably more like a 15-year line. That's the Ausable Chasm. That's a tourist trap just south of Plattsburgh. Not now, it isn't, when it's full of water. Literally, the chasm is full of water. It's a couple hundred feet down to the bottom there. This is the east branch of the Ausable. We've done a lot of work with classes here and a lot of research with the Ausable River Association, Nature Conservancy, and others. Just a quick storm hydrograph. This is the East Branch storm hydrograph. And you can see how quickly it came up, 2 feet to 18 feet. And there's the water line. There's the person standing. The river's on the other side of this road. And then you can see a few other little storm events after that. You can just get a view for what happens in a river in storm events. This was a spate event for sure. Came up, went down, all in the course of roughly 24 hours. And so the flood of record for the East Branch is also this event, the Irene event, 96. Some of you remember that, was the previous flood of record. And then we go back to 38 and then 48 and 79. There's the 20-year line on this graph, discharge over here. And then here's Irene again, way out over here. This is kind of interesting. This is the Stiles Brook stream, this lower picture. And the channel is normally here. And it did what we call a vulse. It basically left its bank and took a new path down a road, essentially cut a 15 feet deep channel down the side of a road. This was a case of a river moving its way through the valley, even though we kind of tried to box it in. There's a little berm here, and that extends all the way down. We did try to box it in Irene told us, you can only box me in for so long. That's that road as of a few weeks ago. It's been replaced, it's been bermed, the river's been put back in its channel. This is a flood probability graph, and I'll just spend a few seconds on this. This is East Branch Ausable data, and what it's just showing you is what's that 1 in 100 year flood event, this probability of occurrence. It's some statistics on the existing numbers that we have in the record. So the 20-year plus occurrence is roughly 12,000 cubic feet per second. Like I said, that's probably more like a 15-year occurrence. And then we have these events out here, and Irene actually would fall way out here, somewhere around, pretty broad range here, 200 to 500 year type event for this river. This is probably, even the 96 flood was right on the 100-year probability. You know, reality is that the data shows that since 1970, 96 is probably more like a 75-year or even less recurrence interval event. We'll know more about that once we get another 50 years of data and it tells us what that recurrence interval is. Much of what happens out on that end of that graph with Irene and 96 in terms of the recurrence interval is largely speculation because we don't have data out there. This is last Friday's exceedance probability graph from the USGS Forecast Center. This is a great website. And you can just look at flood, discharge, and probability that you will exceed. You're way down here to 2% that will even get into remotely flood conditions. So they're using models, and they're basically saying, what's it look like today? You can get on this website, and you can see things on, every few hours, every 12 hours. You can look at this, and it'll tell you what your river is going to do based on historical data, the blue points, or actual data. Okay, Irene, we all know it came up. It blew through the northeast, and this happens to be Essex County, New York, where this pink thing is, and it got pretty well hammered. And that really was the entire Ausable River watershed. Sustained a huge amount of rain in a very small area, and really put the river, and all the rivers in Vermont as well, into this discharge state and stage level that we didn't ever really anticipate. We've built in the floodplain. We've got structures that have been there 80 years, 100 years or longer, and we thought the river will never get to those structures. This is one of my favorite sites. It's a tributary to the East Branch of the Ausable, and it's the old Town of Jay water supply dam. There's a dam right here. It's full, and it had about 4 or 5 feet of water in it up until Irene, which pretty much filled it. It's now a river that runs basically to the edge of the dam, and then it's a waterfall. There's really no reservoir there anymore. Fortunately, Town of Jay doesn't get its water from this anymore, so at least we're good in that. This is what that stream used to look like. I've worked here an awful lot. I'll show you a little bit of biological data from this stream in a second. And that's what it looked like after Irene. You can see the water line up on the trees about the height of the person. It really just blew material out. That's what this river, these events do. They carry material. It's called capacitance, which is the size of material that a certain flow event can carry. In this case, on the Ausable River, we're talking boulders the size of car engines are moving down the stream. This is the biological data that I quickly found this morning on my computer. My class has visited that Rocky Branch site time and time again. I was actually teaching river ecology during Irene. Our first class was August 29th. So we got to go and see rivers like you'd never see them before. In 2007, these are the total densities above and below that little dam I just showed you. About 1,000 individuals per square meter. This is the insect community that I was talking about earlier. And this is basically taken about 2 weeks after the 29th. You can see we have very depressed invertebrate densities. Everything really, the Mayflies, Stoneflies, Caddisflies, everything. The storm really blew these streams out. It was a big disturbance, if you will, for the biota that were living in it. And with respect to fish, similar data, we did have a lot of fish that were below this dam. So they got washed downstream, and as they were trying to move upstream, they were stacking up at that dam. We got really high fish densities below that dam. But fish certainly were probably displaced downstream. Believe it or not, a lot of fish made it through. They find refugia behind rocks. They find refugia from the flow, and they actually live through these types of events. This is a couple more pictorials. This is Deer Brook in Upper Ausable Valley. And we're doing a study on culverts in the Ausable, so we're fortunate that we visited well over 100 sites there We finished it the Friday before Irene. So we have a lot of images from these streams. This is before the storm. Keep your eye on this tree and the tree behind it, and these two rocks with the moss right here. This is after Irene. We're a little closer. There's the two rocks with the moss. There's the two trees. So the channel has changed. You see these rocks there's no moss on them, and they weren't there before. They rolled in the storm. That pretty much tells us what the capacitance of that stream event or that flow event was. It's rolling rocks the size of car engines down the stream. You probably wouldn't want to be there while it's doing that. This is Stiles Brook, one of the sites in the Ausables that really, really got hit. We also have data from this site from before. This is in 2007, where it crosses the highway. This is right after they completed the work. And then if you look upstream, that's looking right from under the bridge in 2007. That's Stiles Brook in a more or less natural channel form. And this is what happened to Stiles Brook after. And one of the things we did is we're trying to help. We go in these rivers and we try to fix things. The river had sorted itself out pretty well during Irene, except for where it ran into a bridge or a culvert and it had to kind of drop its bed load and do something different. Well, we went in and we kind of stabilized the banks and we got everything out of the channel and we made us a nice little canal here. The river will sort this out. If we get another Irene event, all of these small rocks are going to move, but maybe 50 years until that. So until then, we're going to have a nice sort of canal there. It could be worse. You may be in floods in other places. How about the Mississippi River? Winona, Minnesota continually floods. Here's the town in the floodplain. Here's the town. There's the floodplain. What do we do? I mean, it could be worse. We might not be in high gradient mountain systems like this group, or Valmeyer, Illinois, and the 93 floods. And this town's flooded 5 times prior to that. Valmeyer did something very interesting. They took the FEMA money and they moved the town up on the bluffs here. The entire town of Valmeyer moved up on the bluffs. They said, we're sick of flooding. We're going to farm in the valley. We're going to live on the bluffs. Guess what they do in Europe, where they've lived for 2,000 years and they've seen not 200-year events, they've seen 1,000-year flood events. Guess where they live in Europe? They live on the bluffs and they farm in the valley. We might want to take those lessons from our colleagues in Europe. Maybe for a change we could learn something from them. One of the things we try to do is stabilize channels. We have lots of good projects, good geomorphologists out there, we've done this in a lot of places. This is another one of these examples of sort of going in the river and trying to fix it. That's Johns Brook before Irene. This is Johns Brook after. This is in the middle of the heart of the Adirondack Park. There are $1 million homes no more than 200 yards from this river. It's where people come from New York City to play. There's Johns Brook again, a few pictures. Now they've gone into this stream and they've had a geomorphologist come in and they've actually tried to put this back to a more diverse flow regimes and put in some structures to basically, if you take the riprap and you just pile it up like this, you berm it, you're separating that river from its floodplain. It needs its floodplain, not only for some of the biota which need it, but it needs its floodplain to dissipate the energy. If you do this to a lot of streams, what you're doing is sending energy to your downstream neighbor. Your downstream neighbor might not appreciate that when their banks blow out and their town gets flooded. So you might not want to do that. A few more pictures of Keene Valley. There was a lot of destruction in Keene Valley. And I'll make one last point about sort of restoration after the event, which is about this woody debris. There's a lot of it sitting in these rivers. One of the first things a lot of the towns wanted to do was go in and take the woody debris out. And I find it there's a little irony to that because this is good bank stabilizing material. It's going to silt in, it's going to stabilize the bank on that stream. And if you want to get a consultant to come in and fix this stream, one of the first things they're going to do is embed wood in the bank to make stabilizing structures. They're going to charge you hundreds of thousands of dollars to do that. We have plenty of natural woody debris in these streams if we would just use it properly, as opposed to just going in and trying to clean it and remove it all out. That does seem to be our tendency. We want to clean the channel, make it nice, make it like a canal, I guess is one way to look at it. Yes, there's devastation. Oftentimes our roads are right in the path where the river wants to cut. or will cut someday. And so how do we do it? How do we live with these systems? Where do we put our roads? The Keene fire hall is being moved. They realized it was in the wrong place after Irene. It's going to a different piece of property. It's being moved. Irene basically told them as much. And I think I'll stop there.